Hi everyone. So from today we are going to start another chapter, the atom. Okay. So this is the very first class of this topic of this chapter, atom. So today's class will be some kind of introductory class, and we will discuss the history of discovery of the atom, and after that we will discuss the Rutherford model, the planetary model for the atom basically, and the total outline of this topic, this chapter will be like this. The first is we will discuss some kind of historical background, very brief. Okay, after discussing the historical background, we will discuss the Rutherford model, which is also called the planetary model for atom. Then obviously we will discuss Bohr's atomic model, which is very much important. Let's say after discussing the Bohr's model, we will also we will also deal with de-Broglie's hypothesis to prove the Bohr's model as well. But okay, that's good. Then we will discuss the atomic spectra of hydrogen atom. We will discuss that, and also we'll try to make justification of that atomic spectra by using the Bohr's atomic model. Okay, after atomic spectra we will discuss X-ray. Basically this is the brief outline of this chapter, of this course, basically of this chapter. So let me start with some historical background very first. Okay, so we know that we are very much familiar with the Dalton hypothesis, Dalton model about the atom, which says that every matter, if we split any matter into infinitesimal small element, that is actually the atom, and after the atom we can't break any matter anymore. Okay, if we break down the matter, let's say, then the ultimate thing we will obtain, that is the atom. After getting atom, we can't break that. This is according to the Dalton hypothesis or Dalton model. We can say that according to Dalton hypothesis, the atom is unbreakable. There is nothing inside the atom. Okay, it is the minimal block. Atom is the minimal block. Right, according to Dalton. Okay, so Dalton proposed this early 19th century. Let me write it. John Dalton proposed this around early 19th century. Okay, what was the proposition? If we write this explicitly, the proposition was that all matter, if we take any matter that is made of very tiny indivisible that means we can't break down that part anymore, indivisible particles, which is called atom. Okay, this was the hypothesis of Dalton, but we have already studied that this Dalton hypothesis is not correct. It's very much trivial. We can say that this Dalton hypothesis is okay. We have to start with somewhere, right? So Dalton gave this hypothesis that is very much basic and straightforward hypothesis we can say, but after after some decades, after some years, it was proved that this hypothesis was not correct. Basically, there are lots of flaws, and there are very much experimental evidence to prove this hypothesis actually very limiting hypothesis. Okay, so actually atom is not indivisible. It's tiny, it's okay, but not indivisible. We can divide, we can break down, and we can also go into the atom as well. There are various elements remains in the atom. We know these particles nowadays, right? So first, this hypothesis was proved wrong when the electron was discovered. Okay, and this is the end of 19th century. Let me write it. So we can say that around a century, it was considered a very much rigid hypothesis. There was no flaws in this hypothesis. We can say that when the electron was discovered, then it was evident that this hypothesis is not the correct hypothesis for the atom. Okay, so electron was discovered late, or not late, in end of 19th century by J.J. Thomson, right? J. Thomson discovered this electron. Okay, so not Thomson, there was also William Crookes, Joseph Thomson, J.J. Thomson, Phillips Leonard, and others. Okay, how they discovered electron, we have discussed this in the electromagnetic waves chapter. We know this very much. If this is a gas tube, we can say that discharge tube. Let's say this is discharged gas tube. If we consider that discharge gas tube, then if we in discharge gas, electric field is provided through this, in this discharge gas tube. From there, if by doing the experiment, these experiments were done in very low pressure condition. Under doing this, using this experiment, Thomson discovered the electron. We discussed this experiment, right, in the electromagnetic radiation part, electromagnetic waves chapter. I am not getting to that because we have already discussed these things already, and we have also familiar with the results of this experiment. Okay, so I am not getting into that, but we should consider the results. Okay, what was the result of the discovery of this experiment which discovered the electron? That okay, J.J. Thomson basically okay, let me write it first. Discovered the electron, but the Millikan determined the charge of the electron. Okay, Millikan determined the charge of the electron. What was that? Okay, first in Thomson experiment, it was found that E is the charge of the electron, E divided by Me. Me is the mass of electron. This ratio was obtained, and this ratio was, what was the ratio? That is actually okay, 1.76 into 10 to the power 11 coulomb kg inverse. This was the ratio which was obtained during the experiment doing by the Thomson et al. Okay, this experiment, and Millikan obtained the charge by, which was the, what was the oil drop experiment. Charge of the electron was obtained, and that is 1.6 into 10 to the power minus 19 coulomb. This is in coulomb unit, SI unit, and it is also equal to 4.8 into 10 to the power minus 10 ASU. So by using these two results, we can also evaluate the mass of the electron. Which is, it should be E divided by E over Me. if we put these values, then we obtain that this is 9.1 into 10 to the power minus 31 kg. So this was the observation, this was the discovery of the charge of the electron, mass of the electron. Basically we are familiar with the electron by the end of the 19th century. We are very much confirmed that there is a particle inside the atom which is negatively charged particle, and that is called the electron, which is having mass of 9.1 into 10 to the minus 31 kg and having the charge 1.6 into 10 to the minus 19 coulomb. So after this discovery, it's very much evident that we can say this without any dispute, that atom is not indivisible. We can divide it. That's why in atom electron is present. So it's necessary to describe the structure of atom, how the atom is we can say that which model, the model of the atom is appropriate to explain this observation, the experimental results, everything. Also by that time, around the late 19th century or the very first 20th century, you can say that the atomic spectra of the hydrogen atom also very much evident experiment which proves that which was suggesting that atom is not indivisible. Okay, atom is divisible, and that's why you are getting the atomic spectra. Okay, we will get into that later, but first now we have to, when it is clear that atom is not indivisible, there is some thing inside the atom. We can say that the atom is not the ultimate particle of the matter. We can't divide furthermore. That's not correct. So later it is very much important to describe the structure of atom. It's okay. So first J.J. Thomson proposed the palm pudding model. Okay, so first describe the structure of atom. J.J. Thomson proposed the first. Let me write the century. It was given by J.J. Thomson, because J.J. Thomson discovered the electron. After discovering the electron, it is evident that there is something inside the atom, so we need some model to describe the structure of atom. So he first gave this model. This is called palm pudding model. Okay, what is the basic understanding? We can say that after discovering the electron, that electron is negatively charged particle. It's evident. Okay, but every matter is it's neutral. We know that matter is neutral, right? So any matter generally is neutral, but according to the theory of Dalton, or we know that the matter is made by atoms. Okay, question was that atom is the ultimate particle or not? We can divide it, not if we can break down atom or not, that's the different question. But it is beyond any doubt that matter is formed by infinite number of atoms, and matter is neutral. So it's trivially can say that the atom is also neutral species. So if atom is neutral, that means there is no charge of the atom. We can say atom is totally neutral, but electron is negatively charged and electron resides inside the atom. We can say that. So it's straightforward that there should be some positively charged particle inside the atom also. Then overall atom will be neutral. Otherwise, the atom will not be neutral overall. And in that case, the matter should have some kind of charge. Okay, but it's not the case. Around us, everything is matter. Everything is neutral. That's why we can't get any electrical shock. We can say that. So in that purpose, you can say that every matter is neutral, which readily follows that atom is also neutral particle. And as electron is negatively charged particle, there should be some counterpart, positive counterpart of that electron, which has a positive charge, which makes the overall atom neutral. Okay, so this was the basic understanding of J.J. Thomson after discovering the electron, and he suggests that there should be some, we can say that like the palm pudding, we know that the palm pudding structure, the how it looks like, there is, this is the positive inside the atom is pictorially showed like this according to J.J. Thomson. This is the positive interface, and in this positive interface the electrons was like this. These are the electron. So this is like just palm pudding. We know how palm pudding looked like. It's just like this, right? Where this is the positive surface and these elements are the electrons having the negative charge. So overall species is neutral. This is atom. According to palm pudding model, this is atom. These electrons are basically embedded in that positive surface. This is the whole idea, but this is actually not correct. That's why the palm pudding model was not taken care of, because the experimental evidence was not the experimental findings around that time, around the early 20th century, was not be justified by this palm pudding model. Okay. So what was that experiment? We can say the atomic spectra. This was very important. Okay, because around that time, as I mentioned, the atomic spectra was obtained, and this atomic spectra was very peculiar because this contains discrete lines. We will discuss the atomic spectra in details later, but let me say now, like this contains some discrete lines. Here is some line, here is some line, like this. That's why it's called the line spectra. But this line spectra was not justified by this palm pudding model. How the nature of this atomic spectra can be like this? This was not justified by this model, this palm pudding model. That's why this palm pudding model was not considered. Okay. To describe the results, the observation, the experimental observation, Rutherford proposed its model, which is atomic model, Rutherford atomic model, which is also called, okay, I'll discuss in next part of this chapter. But up to this, what was the basic introduction? That first Dalton was proposed some theory of atom, that atom is indivisible part of the matter, but later J.J. Thomson find out the existence of electron, the charge and the mass of the electron, which evidently proved that the atom is not the indivisible part of the matter. So, and as electron is negatively charged, so there should be some positive charge present in the atom as well. And following his observation, J.J. Thomson proposed a model which is a palm pudding model, which says that there is a positive interface, and on this positive interface, the positive surface, the electrons, the negatively charged particles are embedded. And this was the palm pudding model, but this palm pudding model was unable to explain the atomic spectra. That's why it was not accepted for as a valid model of the atomic structure, which explain the structure of atom. So later in next part we will discuss the Rutherford atomic model or the planetary model. Okay, so thank you.